So can we start?
Yes, ma'am. Uh,
I'll take 2 minutes to just introduce you, sir, to the participants, and later you can.
just a minute. The desktop will be shared, right, automatically?
Yes, sir. If you share, once I
Because
stop sharing, so you can share now. You can share the slides, sir.
uh, how can I share it? Sorry, because I have not used. Okay, is it like clicking on the present now?
You're present now in the window, sir.
Okay.
So we will now begin with our sixth section of this FDP. Our speaker for this session is Dr. Manjunath S. To introduce about Manjunath sir is currently working as Chief Engineer at Samsung Electro-Mechanics, Bangalore. Prior to this, he has worked as an Assistant Professor at Central University of Kerala, Kasargodu, and JSS College of Arts, Commerce and Science College, Mysore. He obtained his PhD from the Department of Computer Science, University of Mysore. His topic of research during his doctoral degree was video archival and the retrieval system. His area of interest includes computer vision, machine learning, and deep learning. He has published few research articles in international and national level journals and conferences. Over to you, Manjunath, sir.
Yeah. Thank you, ma'am, for the introduction. Good afternoon, everyone. So today the topic that I have chosen to share with you people is about model drift. The workshop title says Computer Vision and Pattern Recognition Challenges and Opportunities. So normally
Sir, one
in
second.
any yes,
Have you shared the slides, sir? Slides have not been displayed.
yes, yes, ma'am. I have shared that one.
Present now in that any window, the slides window, sir.
Uh, okay.
Slides has not been visible, sir.
Now, ma'am.
Yeah, it's going on. Yeah, sir.
For me,
Yeah, sir. Continue, sir. Thank you.
yeah. Okay. I think yeah. So the topic of the workshop says it's computer vision and pattern recognition challenges and opportunities. So when Professor Harish called me to present on pattern recognition related, I said it would be better if I discuss about once we complete develop a model, how it will be deployed in the production, and what are the challenges we face during the production, especially in case of deploying in the real environment like factories or in real life. So based on that discussion, today I am presenting on a topic called as a model drift. So the outline of the presentation is as follows. So first, I will just give a brief overview about machine learning life cycle in two different scenarios. If I take the example of any this one academic research, where even in academics we create models and we do experimentation on a specific data set, and then publish that work in a journal or conferences. Whereas in case of industry, it's not only about just developing a model, how that model will be deployed in the real environment, and what are the challenges we need. It's about post production. After coming out with the model, how it will be done, and what are the things. Those things will be discussed. So in that, we mainly face the challenges model drift. What is that? What is meant by model drift? What causes a model drift? That will be understood. And also, what are the different types of model drift we have or we face? That will be discussed in the presentation. While explaining the types of model drift, whenever it required, I will illustrate with some examples with a toy data set, and also I will demonstrate on the same thing. So at the end, we will have a discussion, like any questions that can be discussed. So coming to this academic ML life cycle. So here we have let us say in academic ML life cycle, like mainly I am concentrating with respect to a researcher. So there will be a researcher and a supervisor. So whenever we select a problem for research, the data and the problem will be decided by the supervisor or in discussion with the supervisor and the researcher. So we will try to find out with an intention of finding a solution to that problem. We will start gathering the data. So I hope like everyone knows what are the main steps of machine learning life cycle. So the data will be collected, and first step will be the data understanding. We do pre-processing, like whatever the pre-processing steps required, depending upon the data. Like the data can be different. Like it depends on the problem that we have selected. It may be like text data, audio, image, or video, or multimedia data, anything. So we need to understand the problem and the data. So, and in order to come out with a proper solution for the problem, we need to identify what are the pre-processing should be done. Means we need to prepare the data. So, using the appropriate data pre-processing techniques, we do pre-processing, and we make the data ready for learning purpose. So in learning purpose, the most important step is the feature engineering. Like we have to come out with what are the different features which are suitable for our data. We have to identify. We have to extract all possible features. From that, we think about dimensionality reduction. We identify the suitable features, and then we think about which model should be used. So as you all know, in pattern recognition or in machine learning, we have plenty of learning techniques, right? Either it may be supervised or unsupervised, depending upon our problem. We identify the problem learning technique. So henceforth, instead of learning technique, I will call it as a model. The model will be identified and designed based on the feature. So, and on the extracted features, the model will be trained. So we will evaluate the model. So in this process, we will try to split the data into two types, like training data and validation data. Train data will be used for train the model, and validation data will be used for evaluating the model to identify how the model performs, like whether it is good or bad, whether the model has learned properly or not, whether the model has overfitted or underfitted. Those things we need to check. For that, we will try to use this validation data. And this validation data should always resemble the real scenario, means the real world. So with an assumption, whenever we take a data, right here, with an assumption that whatever the data we have in a training set and in the validation set, it will be having some assumptions. We make some assumption. The most important assumption with which all we researcher work is whatever we have the data that will be resembling the actual scenario when it is deployed. Means we call it as a live data. So whenever we deploy any model, the validation set and the live data will be having the similar statistical properties, like the distribution. We can think of any simple distributions like mean, median, or what is the percentile and all those things. So based on that assumption, we will try to evaluate the model. So once the model is ready, right? So normally we use a cross-validation technique to check or to evaluate the model. Or in order to take a decision whether the model is good or not, we use certain measures. Simple measures may be like accuracy or F measure. So if I am not happy with the developed model, as you all know, that we will try to go back to the previous steps, and we will try to tune the model. Like it may be even we can go up to the level of data understanding. If I am not happy with my model, I can go up to data understanding. That's why we have backward arrow marks. So if I am not happy with the model, try to do the training, or you change the model design itself. Means you come out with a new model, or you think about changing the features or pre-processing, or collect more data with respect to that problem. Try to understand the problem properly, do this process. So it's like a loop. Like until I get a perfect model, even in the academic life cycle, I need to do this process continuously. So one thing here I need to emphasize is like while finalizing the model, like to say that okay, model is ready. Normally we think about two things. One is ground truth and the predicted values. So this is very important for entire my discussion. One is the ground truth versus predicted. See, in case of this ML life cycle, if I want to evaluate the model, especially if I am working on a supervised learning, so in the entire presentation, I take supervised learning. We will compare the ground truth with the predicted values, and based on that, we will take a decision, like whether the model is up to my expectation or not, or whether it can beat the current state of the art result. So if yes, then we will try to publish it. So in case of academic ML life cycle, what happens, like once we publish or we finalize everything, that's all. Like it's just like I have created a product and I have published it. So that will be the end of a academic life cycle. So normally we won't deploy anywhere, or we will not check what is the issue, whether it will work properly in the real scenario. So here for us, only it has to be better than the state of the art technique, and it should have the appropriate results. Coming to a production life cycle, production ML life cycle. So here, instead of a supervisor and a researcher, there will be a customer and a data scientist engineer or a ML engineer. So a customer, the overall steps are same. The customer comes with a problem on the data with an expectation to machine learning engineer saying like, I want a model which solves a problem, particular problem. So here the ML engineer also do the same process, whatever we do in the academic life cycle till model production. So once the model is selected, and the next step, instead of publish, what we will do, we will deploy that model into the production area. So in case of deployment, we will be getting the live data. Means once we deploy this model, we will be getting the live data, and we will be having the output. So that's all the difference. Like if you see at the higher level, in case of academic life cycle, we will just publish that, and we will forget. Whereas in case of production, we will deploy the model and we will stop. But this is not the actual scenario. Like it's not a data scientist or ML engineer will deploy that model in the production, and he will forget, because the customer will be in the loop here. The customer will be thoroughly checking how the model is performing. So because it has some impact on his business, right? If the model is not perfect, then it will not work. It will be having the issues. Let us take an example. Like if we take an example of PCB manufacturing, right? Whenever we produce a PCB, before shipping it, we need to ensure the quality of the PCB, and this holds good in all of the products. Like the quality of the product should be up to the mark. So if the quality of the product is not good, it should not be shipped to the customer. It should be rejected. So let's take this example. We have designed a model for detection of defects in the PCB boards. Okay, PCB. Uh, the model, the responsibility of the model is to identify whether the manufactured PCB is in compliance with the standard, or whether it has any defects or not. So when it is deployed in the production, right? So it has to identify whether it has a defect or not. If it is a defect, it has to be rejected. If it is not a defect, it has to be sent for package. So live data will be given to this production. Here, production means not producing the PCB; it is a verification of the PCB data. So this model will verify the PCB data and it will give the output. Like it may be a binary case, like yes or no. So if the model is a good model, right? So it will be accurately identify the defects and the customer will be happy. If the model is not perfect, then the customer will receive a defect PCB or defect products, right? Then it will be having impact on the customer business. So he may lose his business, or there may be a problem or issues in his business. So in that case, we need to monitor this model, like whether the model has any issue or not. That has to be thoroughly checked during the production. It's not like we created, we deployed, and our job is over. So it's a process where we need to identify, is there any issue in the model, or any challenges or problems have occurred in the production line. So there are a lot of challenges in this production line. The challenges are, like, the model may be when we deployed initially, the model may be performing very good. So after some time, like, the model may try to degrade, means the performance of the model may be reduced. See, in case of the model evaluation before production, it's very easy to evaluate a model, because we will be having the ground truth, and we will be having the predicted values. So we will just compare, we will identify how much it has been evaluated and all those things. Whereas in case of production, the ground truth is not available. So I hope you are getting this critical issue. Like, in case of production, we are just producing. There is no one to give you the labeled data. Okay, this is the defect model, whether your model is checking or not, properly verifying it or not. So there will be no ground truth available. So in that case, we need to identify whether the model is performing good or not. So if I take at a higher level, based on the customer review only, I should decide whether the customer is getting any issues in the product, and then I have to take a decision. So it's a very challenging issue. Or it's the same as our human beings. Like normally, let us say, if there is a teacher, like a professor, who is teaching in the right. So with respect to time, there may be issues in his teaching. So what may be the issue? Like let us say, like when I completed my PhD on pattern recognition on a video database management system, and then I joined academic institution. In that case, like I was thorough in pattern recognition or video analytics, or something which is related to computer vision or pattern recognition. But when I was put on to production, like in the academic, it's not like that I will be teaching only pattern recognition or machine learning or video related. So depending upon the curriculum, I need to teach it. So the thing is, whatever I was learned, it's entirely different now. I am teaching it. So normally, what we professors or we will do, we will try to update ourselves regularly, right? It's not like that I will be teaching a particular subject throughout my life, right? So same way, there may be a change in the data which the model is seeing. So when the model was trained, like whatever we had the train and validation data, right, which was used to create a model, that data we expect that the live data will also be have the same nature, but that will change with respect to time. It cannot be having the same data. So if I give a specific example, let us say that I need to identify, I need to create a application where I need to recognize the students moving in the college campus. So normally, what we will do, we will have a let us say we will develop based on the face recognition system. So we have deployed a face recognition. So when I created this face recognition application, I might have taken the data or the student face images of the current semester, right? So let us say it's a 2 years course. So those students which were collected now, it is having the current students which are in the college, right? So there may be change in the appearance of the students after 6 months or something, or the new data may arrive into the system. In that case, we can't expect, like normally the customers expect, okay, once the machine learning system is developed, it can do wonders, right? So, but it's not like that. We need to update the model whenever there is a change in the scenario, or there may be newcomers, like new students might have changed. The system will not be able to recognize the newcomers, right? Or it may be another defect, like after deployment, right? It was deployed in a outside, like a outdoor environment. So there will be having the environmental defects, like it may be sunny, rainy, or other, like it may be dark or it may be bright. So all these issues will try to degrade the model. So these are the challenges that we face when we deploy any model in the productions. So these things has to be identified. Means we need to identify like whether the model is performing properly or not. Okay, and we have to identify is there any issue in the model, there is a decay in the model or not, and based on that we need to upgrade our model. So today in this session, we are going to discuss about this, like how can we identify whether there is an issue in the model which was deployed to perform a particular task. If identified, how it can be rectified, what are the solutions. So in this entire session we will identify what are identify what are the challenges in model and how it can be resolved. So, what is this model drift means? So, as I said, like once the model is deployed in the production, due to different reasons, like it may be a change in the underlying assumptions. So, mainly these are the two reasons, basic reasons. There are several reasons as we discussed. Like one is the change in underlying assumptions. Whenever we design a model, right, we will be having some assumption. Based on that assumption, the model will be created. So about the data. So this assumption may change according to different, like business change in the business line, or change in the data itself, right? Or change in the distribution of the data, or new or unseen data may be presented to the model, which a model may find it difficult to identify. Example, like let us say we are all well versed with our mother tongue. Let us say I know Kannada, English, or Hindi. If someone speaks in some other language like Tamil, Telugu, or Malayalam, it will be very difficult for us to understand, right? Means unseen data. So we are hearing an which is unknown sound, right? What our brain will do that time, it will just neglect it, or it will say, boss, I am not able to understand this one. But in case of this models, when we deploy the model, right, it's not like that. Normally there are two cases. One case is whenever we create a model, if we have a n class problem, so we will be having the n class. So irrespective of the data, this model will classify the data into any one of that classes. Example, like as I said, if I know Kannada, English, and Hindi, if someone speaks Malayalam or Urdu in front of me, what I can say, like as a human being, as I have some part of intelligence, I say, I am not able to understand what you are saying. So can we talk in a known language to both of us? Whereas in case of models, it will not say that one. It will not reject that one. Normally, it will just classify into any one of that category. Example, if I take the famous fish classification problem, which we see in the pattern recognition book of Duda Art, like salmon and a sea bass. If I have developed a model for classification of a sea bass and a salmon, right, the model will be able to identify given a fish as a sea bass or a salmon, right? If some other fish comes into the screen, right, for the evaluation, so it will not reject stating that this is an unknown fish, okay, for me. So it will either classify it to sea bass or a salmon, because that is what the model has been designed. So a slightly different, like if we try to resolve this problem, what we can do is, if it is a n class problem, we can identify n plus 1 class. We can treat it as a n plus 1 class problem. So like sea bass and salmon plus 1 unknown class, we can have a unknown as a new class, and we can expect that the model will will identify the unknown fish as a unknown class. But the challenge in this issue is like getting that unknown class. In order to train, we need to have the data, right? Example, if I take the fish problem itself, so if I'm working on sea bass and salmon, right? So in case of sea bass and salmon, what happens? Like I will collect the data for sea bass and salmon, right? And we will understand the data distribution. We will identify how we will extract the features. Based on that, we will identify the decision boundaries. Now, if I want to add a third class called as unknown fish category, then I should have all possible fish samples in my data set to have this one. So that is very challenging issue. Normally, whenever we develop any model, we will not have this case like n plus 1 case. We always work on the n class problem. So that's what like new or unseen data. Then also the performance of the model may be degraded. So overall, this assumption, change in the assumption of the data, or due to new or unseen data, there will be lot of effects on the pipeline and services, mainly on the services, which may degrade the performance of the business. So we need to identify this one, whether the model is performing properly or not. So let us try to understand in detail. So what are the reasons for this model drift? So there are two reasons. Mainly, we have two reasons. There may be an issue in the data, or there may be an issue in the data, or there may be issue in the way we have designed the model, or the way we have made some assumptions. So the first one is data skewness. So the training data itself may be designed incorrectly. So when I say designed incorrectly means the data which we have collected to prepare the model itself may be inappropriate. Means it not be same as the live data. So just we have taken some sample data, because we will not get the entire population. We have to work on the sampled data for model preparing. So the data which we have taken, it may be not correct. So means there will be a mismatch in the train and the live data. So this will be having definitely a issue when the model is deployed. Or there may be a issue in the data. Example, like if I take our any research publications, right? Normally we will try to take the publicly available data set. Means someone might have created the data set. So using that data set, we will try to come out with the solutions. So whenever these data sets prepared, they will be taken care extremely. Means the quality of the data, like pre-processing of the data, all those things will be taken care while preparing the data itself. So for a researcher, it may not be an issue. Like he may take the data directly, he may use or he may come out with a new approach as a new model, and with good results, and he will publish the data. But when we deploy it and when we are working on the live data, it will be having a lot of issues. Example is there may be a poor quality of the data due to several reasons. Like the example of identifying, recognizing the students in the college, right? If we have deployed in a outdoor environment, due to the environmental changes, right, the data which we are getting may be inappropriate. Or if I take the example of the sensor, like image itself, like I said about the PCB data, or if we are working on the health monitoring of a machine, right? We will be collecting the data from the machine using several sensors. Like it may be a temperature sensor, or it may be a pressure sensor, or a heat sensor, or something, right? The sensor itself may have a issue after certain period of time, right? In that case also data may be having issues. Or let us take even before means the data which was given to us was collected from, let us take example of a temperature sensor. The data was collected from a sensor by company A, right? When it was deployed, in that case, the sensor was different. It was company B. See, uh, it's the same sensor. The sensor is a temperature sensor, but the company is different. So does it make sense? Yes, it makes sense, because the implementation wise, while getting the data from those sensors may vary from a company to company. So it may be like they may be sending the data. Let us take simple example. They may be sending the data in integer. Some other company may be sending the data as a real number, or the precision may be different. The precision may be very small, or precision may be very large, right? Or in that sensor, whatever the features we were able to calculate for the creation of the model may not be able to create in the live data. The reason is some data may be missing, means some part of the data may be missing from that sensor, or the scale of the data. That's what I said. Like different sensors will having the different range of the data. So all things will matter when we deploy the models. A feature is not available in production itself, means when we design the model, like normally we will get all the required data, because we will be working with the customer, or we will be working on the data which have everything proper. But when it is deployed, due to several reasons, like a particular sensor may be not working at particular instant of time, the data may not be available. Because of that, feature may not be able to create it. So we and the model has to predict. So that time we have to there will be a issue in the model performance. These are some reasons for data skewness, like why we will having the issues in the model related to data. So coming to a second case, model staleness, right? There may be shifts in the environment. Like whenever, I gave the example of this one, right? Student example. So for a customer, when it is deployed, right, initially for 6 months, let us assume, it was used for identification of students. Now they want to identify the movements of the non-teaching staff or teaching staffs who will be working in the company. So they see, like for them, it's a very straightforward. Okay, it's based on the face recognition. Okay, if you train, it will work. But there will be a lot of issues in that also. So just hearing that one, it may be appear like, okay, face recognition is whether it is a student or teaching or a non-teaching, it will have same thing, right? So it will not be an issue. It should work properly. Even for any machine learning engineer, it seems like a appropriate one. But it will be having a different issues. Okay, let us take this example of the PCB defect detection. So let us say, now, if I take the example of mobile chips, right? PCB, what we have in this one. So if I have a model M1, a mobile model M1, inside I might be using a PCB1. The structure of the PCB will be something unique. Let us assume. So what this customer assumes, okay, this model is designed in such a way that it will identify defects in the PCB. The structure, like normally if you have seen PCB, we will be having the lines, connections and everything, right? So it is different from one PCB model to another PCB model. If a new PCB model was given as a test case, was presented as a live data to the model which was developed based on the PCB model 1, right? Then it will be having changes. That's what. There will be a change in the environment. Means based on the business, it will be having environment. Even this model will be having the issues. Means as time goes on, the model becomes old, and model will be not adaptable to the new environment. Means either we need, first we have to identify, okay, the model has become old, it is not able to identify. That's what the main challenging things. And changes in the behavior of the model, like there may be change in the target variable itself. Like as I said, like if I want to classify the, if I have developed a model for classification of salmon and sea bass, and if I give a new fish like a starfish, like there is a change in the target variable. Means there are three classes, 0, 1, 2. Earlier it was 0, 1. So this will be definitely having the issue on the model. There are several adversarial scenarios. So adversarial scenarios means it can be anything which cannot be identified prior to model deployment. A very good example is like my model may be performing very good, right? But the machine where the model is running may be having the issues. Like let us take this simple example. If it is based on the image sensor, like where we will capture a image of a particular product, and based on that we will take a decision whether this is a defect or not. So when the image was supposed to be taken, for first 6 months or 1 year, the camera was still. After, due to some changes, the camera is shaking. Right. So in that case, the assumption was we will get a unblurred image. Means a very good image will be given to the model. But due to shaking the camera, right, the movement of the camera is a blurred image. Or even if it is not a shake, due to in the factory environment, the camera may have some dust or something. See, these things, until we go and check, we will be not knowing these things. So these things will affect the model. So the entire thing is like we need to identify whether there is a change in the performance of the model or not. So if we want to do, how to do, that is what we need to understand. Let us try to understand what are the different types of model drift we have based on what thing. So there are basically two categories of model drift. One is data drift, another one is called as a concept drift. So data drift means it is related to the data. Means the data may evolve over time. That is what the example I gave of face recognition based application or fish classification something, where when the model was developed, it was developed for a particular reason due to change in the business cases, the new data may be coming into the picture. That's what unseen patterns are coming into the picture. Or there may be variations in the data itself. There may be no new or unseen data, but in the same data, due to changes in the environment or due to some reasons, there may be the variations in the data itself. Even though the number of patterns are same, number of target variables are same, the data distribution is same, the variations in the data may occur. So these things are called as a data drift. Because of this reason, if model changes, we call it as it's a data drift. Because of the change in the data, the model has been drifted and it is going towards decay. The second, I think this is very clear. Data drift means the model performance has become poor because of a change in the data. The second one is the concept drift. So concept drift is a technique the model may perform poor due to change in the interpretation of the data. So what is meant by interpretation of data? So let us say when we design a model, right? So normally we take the distribution of the data. Very simple example, we will take distribution of the data. We will try to understand the distribution of the data, and based on that, we will try to identify the decision boundaries of the data. In any machine learning, as you all know, the main thing is identifying the appropriate decision boundary. So when was this decision boundary was identified or designed? During the model development, right? So during the model development, we will be having the trained data and the validation data. So that will be given to the model. The model will try to identify the distribution of the data, either in a lower dimensional representation or in a higher dimensional representation of feature recognition. It will try to identify the decision boundaries. So the decision boundary was identified based on the data which was presented at that time. Now, due to some changes, right, that interpretation may itself change. Means the data is same, but the interpretation itself is changed. Means the decision boundary is getting deviated. So very good example is if I take the salmon and the sea bass itself, while developing, normally what we will do, right? So we will try to have equal distributions, right, in each class. Normally we assume that we will be having equal number of samples in each class. Like I will be having some 1,000 samples for sea bass and 1,000 samples for salmon. So now the distribution is identified based on the number of samples. As we have equal distributions, we will get some decision boundaries. So that is what the decision boundaries we have developed in our model. Now, in the live data, what happens? Due to some changes, let us say, we are getting a huge number of samples from the same class variations. So if you take that data and you try to study, the distributions will be different. So earlier decision boundary, which was designed on that 1,000 samples, will be either shifted towards the samples which are having the lesser number of classes. Okay, so in that case, there is a change in the decision boundary. So this has to be identified, and we have to update the model. So I will show you samples of both data drift and concept drift. And I will demo you how this interpretation will change, how the decision boundary will change. Okay, so I hope like you all understood what is the difference between the data drift and the concept drift.
Yes, sir.
Okay. So types of model drift. We need to identify now. So given a model drift, first the problem will be how to identify whether it is a data drift or it's a concept drift. So for that, we will go one by one. We will try to understand one or two cases for data drift identification, and same way for the concept drift identification. So data drift, let us take this example. So here, when the model was defined, it was for two different types of lamps, like red, and another one means a table lamp, another one is a study lamp, let us assume. So if you see initially, let us assume we will be having only two distributions, which is white, and another one is the red color. So orange, let us sorry, yellow color, that we will neglect for the time being. So when the model was designed, the distribution was only white and red. So based on that, the decision boundary, which is shown in the dotted lines, will be used as a decision boundary. Now, what happens if you see the upper line, like which is in the fraction? Let us assume, like we are getting the data for a table lamp and a study lamp, right? And if you see the last four samples, okay. So last from the right side, we have two chairs like a structure. Next to that, we have two lamps, but you can identify that it's in a different color. So the reason for quoting in a different color means just to say that the data has been evolved in time. There is a change in the data. So there are two conditions. One is evolve of the data means the data is same, the lamp are same, but color may be different, or new unseen data has come. So in that case, what happens? The data distribution will change. Now, if you assume like the data distribution will be changed, because the two samples which are lamps of different color, it will be mapping to the red, white color, red color, right? So distribution will be changed, because if I take the feature extraction, like if I worked on a shape and a color, instead of just a shape, if I have added a feature as a color, right? In that case, the red distribution will be having a change with respect to time. Okay? In addition to the new data, a new distribution, new samples will be added. So that's why we have a new distribution of yellow color. Now, the model which was designed, it was based on the red and white distribution with a dotted line as a decision boundary. Now, when we use such samples, like a change in the data samples or an unseen data for the samples, right? Definitely, there will be a problem in the issues. So this has to be identified. How can I, like a machine learning engineer, can identify automatically there is a change in the live data? That is the main question. Like once it is deployed, right? A machine learning engineer or someone who has designed the model can't go and sit in factory and identify these things. So for that, we need to just study on the data part. So how it can be done? Let us see. So one is comparing the distributions. We can identify there is a drift in the data because of which the model is getting changed. Like if I take this example itself, like I need to collect the data in a regular interval of time, and I need to identify the distribution. Like just you keep a distribution of previous data. Previous data means which was used for training and validation, and you regularly take the data distribution, or you calculate the data distribution and on the live data, and compare those two distributions and take a decision. Okay, there is a change in the distribution of the data. Because of that, there is a change in the this one, the decision boundary, and hence there is a change in the model performance. So how we will do? Let us try to understand. So training data. So normally whenever we create a model, right? So this model will be having train data and a validation data. So train data will be used for model design, whereas validation data will be used to validate that model, as we all know. So this train data and validation data will be having a distribution. Right? So either you can take a validation data or you can take a training data. So estimate the statistics, the distribution statistics. Uh, you can extract a simple statistics like what is the mean variance or what are the percentile. Just using the some plots and everything, you can get that information and store it in a repository. So that's why I have a data distribution statistics. And also one more thing, like whenever you do on a model, right? So does not only give the target labels, like a given sample, it will not say whether it belongs to class one or it also out with a probability value with the value of 0 to 1. It says that okay, this sample belongs to class one with this probability value. So that is called as a score. So we have the distributions. Now we have two distributions. One is the distribution of data, the statistical values of the data distribution. It can be either training data or analytics. On the other way, even I have the score distributions. Distribution means like if some in my some data,
Sir, Manjunath sir,
yes, ma'am.
sir, your voice is bit breaking, sir.
Clear?
Sir,
Mm. So not able to be
it's bit breaking, so it's not clear yet.
okay. Just a minute, I will. Hello, ma'am. So you are able to hear me?
We can hear you, sir. We can hear you.
Now,
Slides is not been displayed, sir. That's it. We can
yeah,
hear you.
I'm, yeah, okay. So now you are able to see my slides.
Yes, sir. Yes, sir. Clearly, sir.
Okay, so we will be having two distributions. One is data distribution, and the one is the score distribution. So then the model will be deployed. So now after deploying, in the deployment, like we have to obtain the same distribution. Like getting a score is not an issue because it's not dependent or anything. So we don't need any ground truth or anything. So score, irrespective of the scores, irrespective of the labels, we will get the score. So using this, like comparing these two, we can identify whether there is a drift in the model or not. Means once the model is deployed, right, we will be having the benchmark distribution, which is the distribution from the obtained from trained data and validation data, and a real world distribution, it is a live data. So we can compare these two using some statistical test or something, and take a decision whether there is a drift or not. So what we will do, we will try to compare the distributions, and we will get some values. So based on that, we will try to give alarms to the engineers. Like, okay, there is a change in the distribution. Now it is the model is getting drifted. So you should take care of this now itself. Or the second level, the final level will be the model has been already drifted. So there is an issue in the model. Take care. So normally these kind of things will be done. So for that, we have a simple statistical test called as popularity stability index, which gives the information whether there is a change in the distributions of distribution, two given distribution are same or not. So if you see at the bottom, right, so there is a small table. So it says if if you take distribution 1 and distribution 2, and if you do this popularity stability index, it outputs a value. So based on that value, we can take a decision whether there is a change or not. Let us say the output value is less than zero point 0.1. We can say that there is no change, means insignificant change in the distribution, no need to worry. Or if there is if the value is between certain range like zero point 0.1 to 0.25, we can say there is a minor change. If it is greater than 0.25, we can say this is a major change. This is what the standard range for this PSI. Okay. So now let us see how this PSI value is calculated. So what we do, like let us take that I have some 100 samples. Okay, 100 samples in the training data set. So now I will take the 100 samples, and we will try to make it as a bins. Like we will try to identify the score. The score value can range from 0 to 1. So 0 indicates that it belongs to it's a negative case. 1 indicates it's a positive case. Means it is correctly classified, or this one means the classifier is confident that it is correctly classified with a score value of 1. So we will be having the range from 0 to 1. If you see the table, like the first two columns, like max and mean, so it ranges from 0 to 0.99. We bucket it, that one means we will bin the score values with a certain range, like 0 to 0.09, 0.1 to 0.19. I am reading from bottom to up, like that way. So we can create a bins. So now I have a bins. Now, totally it has a 10 bins, like 1 to 10 bins. Now, what we will do, whenever we do any testing, like in case of this one, if I want to understand the training distribution, Like if I have 100 values, I will I will give each sample and I will get the score, and I will check whether that score belongs to which range. Like let us say if it belongs to in the range of 0.99 to 0.91, then I will increment in the training distribution, right? So each score will be checked whether it belongs to a particular bin or not. Based on that, I will get the values. So it's just a frequency, like it's just we are calculate the frequency with respect to each bin. So that is what the training distribution. Now serving distribution, this serving distribution means like on the live data. So same number of samples will be taken, and the scores will be calculated, and the frequency of the scores will be obtained with respect to each bin. And we will be having the two variables like S and T, where S is the serving distribution and T is the training distribution. So if there is no change in the distribution, definitely it will be having a less difference. So this PSI, if you see the formula on top, like PSI, right? First part, it calculates the difference between the actual and expected. So here we should not confused with the actual and expected, means the target variables. We are not checking with the target variables. We are checking with the training distribution and the serving distribution. Here in the entire test, there is no role of the target variables, because that we will not get in the live data, right? So now actual means T, and expected means yes. So we will try to find out the sorry, I told in reverse. Like actual means the live data, and expected is the T. So we will calculate S minus T, the thing, and we will get the column S minus T percentage. And the second one is just to normalize that one using the logarithmic value. So we will calculate the logarithmic value, and for each bin we will calculate what is the PSI index, popularity stability index. So for each bin we have the PS index now. Now if I take the sum of that, like the formula says, take the sum. We have a summation here. If you take the sum, you will get one value. So based on this value, now we can decide, okay, there is a change in the data distribution or not. So this is very simple and method which can be used to identify the data drift. So I will just show a demo, like a Python program, how this will be read. Like, yeah, we have time. We will show that one. So you're able to see the code, right? So I have opened in a Jupyter notebook the PSI walkthrough.
Sir, code is not visible, sir. The slides are visible.
Okay. Stop sharing. So here it's showing, it's not so now.
Yes, sir, it's visible. It's visible, sir.
Oh, okay. So this is just a simple code, like based on the random values. So using another code, right? So here I am trying to generate two distributions, like initial distribution and new distribution with the same number of samples, like 100 and 100 samples. And using the Seaborn package, I am trying to plot the distributions. So whatever I explained, the same thing has been implemented here in this code. So I will try to show you like uh, how will be the results. So let us say like based on the random data which we have generated, the new and this data, like initial and new data, this is what the distribution looks. So we will try to normalize, we calculate the binning and everything. So we will try to just run. So this is the distribution, like the frequency distribution or bucketing, like in each thing, how many values, like initial percent and new percent we have. So this is the bucket versus the population percent. So now you can see that almost it is same. So we will try to calculate the sum of the PSI. So the PSI, it is about 0.166. So according to our this one, if it is less than between 0.1 and 0.2, we say that there is a slight change. So yes, this is what we can understand. So in order to change this one, what I will do, I will try to change the distribution with different things. So I will try to add so now there is a slight change in the distribution. So it has given 0.09. So probably like it depends on the data, how it has been generated randomly, because we are using the random data. So if you try with different options, right, we can get this value. So this will give an hint. Now using this hint, what we can take a decision. So how can I share back to my presentation?
This will be the present now.
Okay, present window. So with this value, we can generate an alarm to this one. Means normally these things will be included at the edge, or either we have to log all the scores in a server, and we need to create one application where it will display these status regularly, and based on that it can be intimated to the responsible person. So this is an example when we have a use case of normal data. Like if I have an image data, normally people works on the image data. So how can I identify the data drift? So I went through some of the blogs and articles, like in one of the blog they have this one, like they have published this also. What they have done, they have used a simple concept of encoder and decoder using deep learning. So this encoder and decoder in deep learning, it is the name is auto encoders, where we will try to represent the data into lower dimensional representation. Means we will transform the data into lower representation using the encoder technique. Okay, and then using the decoder, we can decode it. So using this, they have identified to check whether there is a data drift or not. So it's a very simple technique. So what they will do, so they will take the validation data set, like take the validation data set, try to encode it, okay, and decode it. So now the resultant images, whatever we got it from the decoder, so we are going to check what is the reconstruction loss. So initially we had the original data using the encoder, which was created based on the training set. The validation set has been encoded, and then it has been decoded. So as a output, we have the new images. So the input validation images and output validation images are different actually, strictly telling. So there will be some loss. So that loss will be used to identify whether there is a data drift or not. If we have the same type of images, right? Let us take the example of MNIST dataset. Like most of you may be knowing this MNIST dataset. This MNIST dataset is a digit dataset, 0 to 9. We have around 70,000 images, right? So we will identify what was the loss when we used the validation dataset. Whenever we get a live data set, right? So live data set, we will use the same process in the backend. So encode the live data set on the encoder, which was designed based on the training data set, decode it, calculate the loss. If the data set is same, if there is no change in the data distributions, right? So the loss will be very less. If there is a change, then there will be a huge loss. So then comparing the loss of the validation data and the live data, we can take a decision whether there is a drift in the data or not. So this is what the overall diagram it says. So compare based on the reconstruction of the data. So as I said, like I will just skip this one. So we will be having a decoder loss estimator. So initially we should have a in the database or in the server, what was the loss when we decoded the validation data set. So whenever the live data comes, so live data has to be encoded into a lower dimension and it has to be decoded and estimate the loss. Compare the loss with the validation loss, means validation decoded loss, along with the live image decoded loss. If there is a subtle difference, then you can come to a conclusion, yes, there is a loss. So this can be taken as a data drift. These are the two simple techniques which will be used for data drift. So based on that, we can say there is a data drift. So next, I will move on to the concept drift. So as I said, like in case of data drift, we will try to identify whether there is a change in the data. Whereas in case of the concept drift, it will be based on the decision boundary. Because we are discussing about supervised learning, I am taking the decision boundaries. So in this diagram, I will try to make it clear what is meant by concept drift based on the decision boundaries. So normally when we at an instant of time t1, let us say, when we design the model on the actual data, so it's a well separated data. So you can see that there are two classes, A and B. So based on that, the decision boundary has been identified. So because it is a well separated data, the data decision boundary, here data decision boundary means, let us take an example like a human being writing that decision boundary. So model decision boundary means boundary obtained by the our model. Now, because it was in the beginning, like we tuned the model, trained properly, and we will try to estimate in such a way that the model decision boundary is equal to the data decision boundary. Yes, now I am happy with the decision boundary, so I have deployed it. So after certain time, like let us say T2, due to change in the data, right, right. So like new data may be added into the samples or something, or the way of interpreting the data might have been changed. Now the model decision boundary will be same. It will not change. Whichever we are showing in the blue color, it is the model decision boundary. So it will be remain change. But due to change in the business line, the actual decision boundary has been changed. Means there is a new decision boundary. So this is what we call it as a concept drift, because due to change in the interpretation of the data, the boundary might have shifted. Right, like example, maybe like adding the new samples or something. In that case, we need to identify whether on the new data, whatever we have got, whether there is a change in the distribution or not. But this is not so easy. Like in case of data drift, we took this one, right? The histogram of the scores, right? Based on that, we calculated. We have to use some tricks because in real data means when we get for the live data, we will be not having any control on the decision boundary. We have just deployed the decision boundary. That is what the model decision boundary is fixed. What we have to do is we have to take the data from the live data, we have to do some analysis, and based on we have to get the decision boundary. So we will be having two decision boundaries now. The model decision boundary, which is in deployment, and a new decision boundary. And then we have to identify whether there is a change in this decision boundary or not, and take a decision. And we will say that okay, there is a change, there is a concept drift. That's why there is a degradation of the model. So this is what a simple example. Like when we took the exam training data, this was the distribution, and based on that, we have identified the boundary. Now, due to change in the distribution of the data, like if you see whichever we have in the block, right, dotted lines, there is a change in the population. Like more number of samples are from the red category. So due to that, the distribution, if you see, the distribution is changed. So that's why when there is a change in the distribution, even this decision boundary will be tweaked. So normally we have a question like just seeing the diagram, we may not be able to understand why this distribution is getting changed when I have the same sample. Because when I deploy, right, there is no change in the structure of the data, right? But there may be, whenever we say that whenever we get more number of samples, it's not like all the samples will be in the same structure or a same shape or a same color. There may be some changes. Because of that, the distribution will be changed. I hope you are getting this point. See, for any machine learning engineer, once it is deployed, he will be not bothered about the distribution. He will be always bothered about the decision boundary. Because I expect like I will be getting a table lamp or a study lamp, right? So when I give a study lamp, it will based on the distribution whichever we have in the left side, right? It will identify and it will do it. But when I am getting the table lamps continuously, because the underlying assumption was like there will be no change in the structure of the data. Right now, in the actual deployment, in the live data, we are getting more samples belonging to the table class, means table name lamp class. Because we are getting, there will be lot of changes. Means due to a change in the production, like we discussed right previously, there may be slight changing in the production structure, like a table structure might be say, different. So that's why we will be having change in the distribution, means feature distributions. So that's why the decision boundary will be changed. So we need to identify that one. So what are the different types of concept drifts we have? Let us try to understand. One is abrupt, means suddenly change. Like if I want to tell you the example of a sudden abrupt with respect to this lamp itself, like when we designed the model, let us say like we had the red and gray color lamps. But during the production, there was a change in the business requirement. They said that, okay, we will change the color of the lamp from red to yellow, right? The structure is same, but the color of the lamp is different. Now, definitely there will be a change in the distribution, right? Because I have used both shape and the color features, right? So that's why that suddenly it got changed. So that is what called as a abrupt change. Okay, the second one is a gradual change. These things, gradual changes, will come in a different format due to sensor readings or change in the environment. So because of something else, right, there may be a change in the gradual. Same way we have like incremental, recurrent, and blip. Incremental means so that changes will happen very slowly, means with an incremental. It will not be either sudden or gradual. So it will be unwanted. Recurrent. So this can occur. Like if there is a problem in the production machine itself, this we have understood clearly. like we may be manufacturing the PCB boards or MLCC chips or something, right? If there is a problem with a particular machine, then we will be getting the data with a different format, which will be recurrent based on the lots and all those things, right? Or it may be spike, like there may be change in the data or something in a different spikes may come. So these are the different types of concept trips we have. Just this is for your information, Varsal. So now let us see how we can identify the solution concept drift. In that case, the left side we have the life cycle of a model. Only thing is we need to have a new things in the maintenance part or during the monitoring. So check whether there is a change in the data, or check whether there is a change in the feature distribution itself, right? And based on that, you take a decision whether we need to adapt to that change, or we need to remain with the same model. So if there is a requirement, okay, change to adapt to the changes, then we need to update the model, and we can improvise the thing. So overall, in concept drift, the main thing depends on these two blocks, like change detection and adoption. So change detection, it will try to identify whether there is a change in the data, means there are any new unseen data, or the data may be same, but the structure of the data may be different, or features may be different due to some business cases or something. Based on that, we will try to identify the concept drift. So this is what I want to show you, like the same thing which we discussed earlier, based on the decision boundary. So what happens, like if you see the right part, right? So I have in the right, I have one image which shows the degradation of the model performance with respect to time. So we should have a alarm or something where when it comes to a particular range, let us say accuracy. Let me take the y-axis as a accuracy. If the accuracy is lesser than some 0.92, update the model. Okay, so then we will wait till the performance of the model will be changed. So then we will identify whether this is a reason for a concept drift. So if there is a concept drift, update the model and make it so that it will be having the better performance. So this will be in a regular interval of time. So these things we can implement, and it's a very simple, like concept drift. What we can do is you can use some statistical properties. So today I will just discuss about two simplest techniques. One is called as drift detection method. Another one is early drift detection method. So this drift detection method works very good for abrupt drifts. So what they will do, they will try to take the scores, the errors, and based on that, they will try to identify the mean and standard deviation. Normally, these errors will be in we assume that it's in a binomial distribution. So we will take the simple case, like based on the history data, what we can select the error distributions of minimum and minimum with respect error minimum and error variance minimum. So that we will be having. So at a particular instant of time t, so we will calculate what is the error and what is the variance in the error, okay, based on the scores or something, and we will try to compare this warning. We have a here warning here. So if the current error and the standard deviation is greater than the p minimum plus 2 sigma minimum, this is 2 sigma minimum, then a warning will be issued, like there is a chances of drift. Okay, if I come to the second level, the drift level, if it is greater than or equal to p minimum plus 3 sigma minimum, then we can say that already there is a drift, and we can update the model. This techniques works very good for abrupt drifts. So there was another work, early drift detection. So where they come out with an idea, like based on the same parameters, but with different values. Like if the value is less than 0.95, let us say the accuracy or this overall value seems to be different, then you can give a warning or a drift level. I have the code for this one. Due to time limit, I will skip that one so that I can complete this presentation. So using some statistical process, we can identify whether there is a drift or not. So there are different techniques also, like windowing approach. If it is a time series data or a streaming data, windowing approach is there. So based on that also, we can calculate whether we have a drift in the concept or not. So this is what, like we need to identify the drift. So now the question comes, okay, now I got a information like whether there is a drift, there is a possibility of occurring a drift, or already drift is occurred. So then what I need to do? It's simple, like we have to update the model. So update the model means take the model which is in deploy, retrain the existing model, okay, design a new model. Means with if there is a data drift, definitely we have to do the retraining. That's enough, I guess. Like in case of data drift, retrain the model with the new data, these things, then the model can be deployed. So if it is a concept drift due to business changes like addition of new or something, then we need to train the model. Either you can think about using the same model or come out with a new model. So this is what. So overall, after detection, in both the cases, we need to update the model. Now the question comes for any thing, like why we have to do all such things, like why we need to do identify the drift, and is it simple like where we will try to update the new model, we will try to collect the model in a regular interval of time, and we will update the model. So that is the simplest approach, but that will be having a lot of issues. The main issue is like if I want to update a model, let us say every 6 months I will update the model, whether it has a drift or not. And then it is a additional effort for the company as well as for the engineer. We don't know whether there was a change in the model, means the degradation model is degraded or decayed or not, right? Simply we will try to update. So updation for us, it may be very simple, but when it comes to updating a model, we need to get the label data. The main challenging thing in any machine learning is getting the labeled data, right? So too much of effort and too much of money has to be spent on getting the labeled data. So that's why what we will do, we will try to identify whether there is a drift or not. If drift, or if it is getting into the model is getting into a drift, then only we will go for model updation. So these are the things that I thought of sharing with you people. So mainly I have gone through some of the YouTube links and also some blogs, and based on that I have prepared this presentation. However, actually we are using this model drift in our project where we need to identify whether the machine is having a proper response or not. So we have deployed the models in several machines. We need to identify that machine is running properly or not. For machine monitoring and manufacturing, we use things. So there we are using a different concepts. Same, it will be based on the statistical measures. We will collect the data, these things. So here the most challenging is it's not only about one machine learning engineer and a customer. Like there will be many things has to be involved. So we should have a proper tools. Coming to the tools, like logging the data during the live data, we can think about using Prometheus database, or we can think about different tools. We have a concept different tools in Python which can be embedded directly into the system, into the edge system. We can log it, and we can show it on the dashboard, and we can generate the alarms. We can send emails or notifications to managers and data scientists, like okay, there is an issue in the model, try to update these things. So this is what I planned to share with you people. I think if you have any doubts or anything, you can clarify, or you can send me a mail.
Thank you, sir. Will participants, please, do you have any questions you can ask, sir? Sir, two of the participants are asking for your slides, sir.
Yeah, I will share with you the slides as well as the codes will be shared with you.
Thank you, sir. Thank you.
Yeah, and I thank Dr. Arish and Rupa ma'am for giving me an opportunity to share my knowledge with you people. And for all participants, thanks for your patience listening. And also, like if you have any doubts, you can send me a mail at any time. Thank you all.
Thank you, sir. Thank you for coming here and sharing your knowledge. Thank you, sir.
Thank you.
Sir. Sir, so as sir has told us, once he shares the slides, I'll be sharing to the same mail ID which you have been registered. So we'll end for today and we'll rejoin again in the morning session, tomorrow morning session, that is day 3, session number 7. Share will be linked by 9:30 tomorrow. Tomorrow we'll be having Suraj sir from Surya Prakash sir from IIT Indore, Deepak sir from IIT Dharwad, and Mohammad Javed from IIIT Allahabad. These 3 professors will be delivering the lecture tomorrow, and link will be shared by 9:30 tomorrow. Thank you. We'll wind up for today and meet you all tomorrow morning.
Thank you, ma'am.
Thank you.